moving air carries both heat and moisture. And the important thing to realize here is that air can carry substantially more moisture than through a building envelope assembly than you would get through diffusion. I'll make that point later. And the air leakage in buildings is driven by pressure differentials between the interior and exterior. Where do those pressure differentials come from? Wind pressure and suction on the facade, stack pressure, which is the natural tendency of warm air to rise up in a building and colder air to infill below it, and then our mechanical systems pressurize and depressurize the building. So what does that look like for a historic building? We have sort of a generic brick masonry wall. We have interior, we have high interior pressure because the curators would like to have positive building pressure. And because it's a historic masonry wall, it's got a crack or an opening in it. And our dew point, here's the merit of 1 time the dew point calculation, right, is somewhere in the middle. And if we have high building pressure, we get condensation in the wall. And that's why, when you have a historic building, it's a lot nicer to run it at negative building pressure in the wintertime. Right? Analysis tools, infrared thermography. We heard a lot about that yesterday. This is a nice historic 2003 natatorium in West Virginia. It has a tremendous air leak. And that actually led to ice lenses forming on the exterior of the wall. The interesting thing about, or the important thing about infrared thermography is, again, it's another qualitative tool you can use to look for air leakage. Very tough to quantify, right? What's actually going on here? Better as a qualitative tool. And the best time to use it is if you have a lot of contrast between the warm building and the cold exterior. You can see I took this picture in February of this year, and when it's tremendously cold, and you can see just that the hot air is flying out of the building. Good analysis tools, but I don't know if the gentleman who was in the church yesterday with the infrared camera, he was sort of holding it up in the church, and there was not enough contrast there to really read anything. And that's why when you look at buildings, you got to get up at 2 in the morning in January and carry your infrared camera out there. September just won't work. Okay, vapor diffusion versus airflow. This is just an illustration of the point that I made earlier. Airflow carries a lot more moisture across a building envelope potentially than diffusion. If I have a building interior at 70 degrees Fahrenheit, 30% RH, no vapor retarder, I can get accumulation due to vapor diffusion at just under ½ pound per square foot per month. Enough moisture, certainly is not something to be not worried about, but it is dwarfed by the potential for moisture accumulation from airflow. So if you just, this example, if you have exfiltration at 2 cubic foot per minute, which you can get with just a 9 mile per hour wind on the building, and you have a square inch of opening in your envelope, like you might have at your electrical outlets, right, when they're really drafty in the winter, you can accumulate 26 pounds or more of water in that wall system. And again, this is not quantitative, right? This is just to show you how much more moisture you can potentially accumulate by having a gap in your envelope that moist air just flies through, right? Okay, applications to historic buildings. I'm running out of time here. The most common thing people ask you, well, I got this historic building, I'd like to add insulation to it. Right? I want to have a more efficient thermal envelope. That's probably 90% of the questions that I get about historic buildings that have to do with energy efficiency. So we're going to talk about that first. Just to illustrate that, here's a woofy model of an uninsulated wall. Here we look at the temperature. And one thing that of note here is, right, we're going again from the exterior on the left, interior on the right, 0 degrees Celsius, right, that's where things freeze. And it tells us that the interior half of the wall doesn't freeze at all throughout the year, right, because it receives beneficial heat from the interior. And it also tells us that the wall dries out during the summer. That's tough to read from this slide because you actually have to do a bunch of these and show the accumulation as it progresses over the year. Now, if I add to that same wall, right, if I add to that same wall interior insulation and a vapor retarder, all of a sudden, most of my wall, right, actually up until I get here, freezes during the winter time. And what's really more dramatic is you get this sort of bell of moisture, you know, on the interior where you have the vapor retarder. And that, of course, is just a substantiation of the hunch that we all have that, you know, it's not a good idea to put insulation and vapor retarders at the same time on the interior of a mass masonry wall. Because why? You get freeze-thaw damage in wet masonry. Freeze-thaw damage happens by expansion of water. We all know that as water goes a phase change from liquid to solid, it expands 9%, and it also happens by hydraulic pressure in the capillaries of the material. As the water gets super cooled, it expands and sort of starts crunching into available space. The important thing to keep in mind is that the freezing alone may not cause the damage. What you really need is the material has to be wet, right? There has to be water available, and the more water, the worse it is. And you have to get this destructive cycling of the freeze-thaw action. And this is actually something that you can calculate for specific components as you evaluate what to do with your exterior walls. And to show an example of that you can do with WUFI because it contains weather data. And what I have here is just the horizontal line. The big red line is 0 degrees when it freezes. The purple zigzaggy line is temperature on the south elevation of a building, and the dark zigzaggy line is temperature on the north elevation of the building.
Does it take into account radiation, solar radiation?
It does, because right, it's WUFI. So if you zoom in on those things, you can see that the dark north elevation line just, you know, stays frozen quite a while, whereas the south cycles through there and it experiences a lot more freezing and thawing cycles. Again, something that we intuitively, you know, practitioners sort of have thought about a long time. You get more freeze thawing in Washington, D.C. than you probably get in Ottawa, right? But this shows, you know, some analytical underpinning to that. You can also look at total water content. Again, this is something that's derived from WUFI on the south elevation. Relatively low, and on the north elevation it's higher, and that of course has to do with the fact that on the south elevation, when you get more solar radiation, you tend to get more beneficial drying. So again, you have sort of competing things, right? On the south elevation you get more thermal cycles, but it tends to be drier. On the north elevation you get fewer thermal cycles, but it gets to be wetter. So what's a person to do? Right? Rotatable, that's right. Again, what happens when we put insulation on masonry? Again, another analysis you can run with WUFI. You put a 2-inch semi-permeable insulation on a brick masonry wall and a 6 mil poly vapor retarder, right? People still do that. So some of my practice is based on the fact that people still do this. You put a monitor point there. And then you start looking at the relative humidity on the interior side of the insulation. And if you have semi-permeable insulation, the relative humidity actually behaves, right? And it only goes to about 65%, right? Reasonable, we can live with that. But then once you start adding the vapor retarder, it just goes through the roof, right? Because the water tends to accumulate there. This is on the north elevation. And it's even worse on the south elevation because you get that vapor drive from the sun that just really pushes it into the vapor retarder. Again, some analytical confirmation of what practitioners have sort of intuitively known about for a long time. You can also look at the moisture levels on the interior white of the brick. It doesn't really much matter what type of insulation you use. You get moisture accumulation there.